What does iOS 9.3 and the Nintendo Switch have in common? They both use the browser engine WebKit with a version that is vulnerable to a known memory corruption vulnerability. Remember the news of the Pegasus malware for iOS, which was discovered when it was used in a targeted attack against the human rights activist Ahmed Mansour? That malware used a WebKit exploit as the first stage to gain arbitrary code execution. QWERTY and the Pangu team then used this bug in their Jailbreak Me website, and it turns out the browser of the Nintendo Switch is so old that it also has this bug. And this is what a lot of people are using right now as a first entry point in hacking the Switch. Obviously, the whole jailbreak is extremely complex, even just getting code execution is insane. But I spent now quite some time understanding the bug itself and the first crucial part, which will create an arbitrary read-write primitive. So you can overwrite anything in memory, for example function pointers, but let's start at the beginning. First, we need to figure out how to access the browser in the Switch. You may have heard that the Nintendo Switch does not have a browser. So what the heck am I talking about? Well, there is no good browser implemented, but it turns out that when you connect to a Wi-Fi, which requires you to log in a captive portal, it will use a browser view and load that page for you. A captive portal is common in hotels, airports, and so forth. So we have to figure out how to load our own website here. When you look at the network settings, you can specify a proxy server, which is great because then I can run a proxy server on my laptop and intercept all the traffic. I use Burp Suite as my proxy server and just have to make sure it listens on all interfaces, so other devices on the same network can use it. So now we just have to enter the IP of this laptop into the proxy settings of the Switch. When we now connect to the Wi-Fi, the Switch will establish a connection through this laptop. And we can see here in the burp history view that the Switch tried to contact contest nintendowifi.net. That site just responds with a simple string that the connection works. It uses this to check if you have an internet connection or not. So if this check fails, it will think you first need to authenticate from a captive portal. So next we need to redirect this request to a different page, basically our captive portal. We can do that by simply modifying the etc hosts file to point the contest domain to another IP, for example localhost. Then we spawn a simple web server on our machine, for example with php-s. We can place an index.html file here to verify that this works. And with the browser we can see that we now on localhost have a web server running. So when the Switch now connects to the Wi-Fi, it will try to contact contest and it will go through the proxy on my laptop. My laptop sees in the etc host file what the IP for contest is. So the proxy will connect to localhost instead, which will access our index.html file. Now let's try it. We connect to it, it will check if there is access to the internet. It didn't get the expected result for contest back and it tells you have to log in. When we now press next, it will load what it thinks is the captive portal. Now we have access to a browser that loads our website. So now that we have that set up, let's read a bit more on the WebKit bug. It was assigned CVE 2016-4657 and has the description WebKit in Apple iOS before 9.35 allows remote attackers to execute arbitrary code or cause a denial of service memory corruption via a crafted website. The description can be a bit misleading, makes it sound like it's only an iOS issue, but it's generally a WebKit bug and would affect anything that used that particular WebKit version, in our case the Nintendo Switch. Also, this is not an exploit where you just type into Metasploit, use exploit Nintendo Switch WebKit. This is something where you actually have to understand it quite in depth to be able to use it. Now, let's take QWERTY's Jailbreak Me code, which uses the WebKit bug, extract the first relevant part and adapt it to the Nintendo Switch. I won't go through all this process because that took me ages to understand, but I want to show and explain to you what I got now. So, let's walk through it. First we create a typed array of unsigned 32-bit integers, And in memory, this will create a struct with a couple of different values, such as a JS cell, which contains a couple of interesting values, like the structure ID that determines the kind of the type of this object. We will have a later look at this again. A butterfly pointer, which is used in a bit more complex object, but not quite relevant for us right now. A vector, which contains a pointer to a chunk of memory that represents our array, and the length of that memory. So that array gives us basically access to raw bytes in memory. Obviously, you can't access beyond its length. Then we create a more flexible array, a standard array like you might use. That array is a bit different as it can contain arbitrary types, any kind of objects. So instead of just pointing to raw memory, it points to more complex objects called JS values. And here's an example of the integer with the hex value for 1414141. It would store FFFF000 before it to indicate the value is an integer. Look at the amazing frac paper if you want to know more details about these JS values. In the case of the exploit, it will set the first element of the array to a big array buffer and the second to some number. An array buffer is also access to raw bytes. Basically, different typed arrays can point to some buffer in memory. So if I'm not mistaken, the first element of the array is now a JS value with a pointer to an array buffer. Next, we create a simple JavaScript object and override its toString function. That function is called whenever you want to get a string representation of that object. So if I return 1337 object as a string and I would alert this object, it would call toString and show me that one. But in this case, the function does a bit more. It first sets the reference to the array we just created to null, as well as setting another property to null. In a second, you will see that this stale property is also a reference to the R array. Theoretically, now all references of the array are gone and the garbage collector can free that array. To force the garbage collector to kick in right now, we can use the function which just allocates and removes a lot of objects. And when you do this a couple of times, you can be fairly certain that the garbage collector did some work. After the garbage collection, the function will now allocate a lot of new uint32 arrays. The reference to those are stored in buff, so we can access those arrays. And if everything goes well, those arrays might be allocated where the previous array was. But how is this object with that toString function used now? We define an object that we use as properties, and I think we allocate more than just two, so the properties are not stored inline, but I'm not 100% sure here. Anyway, one of these properties is called stale and is set to the array reference. That is the property that the toString function will set to null. Another property is the length, which is set to the notNumber object. Then we create a new empty array target and apply those properties to it with object-defined properties. This means all those properties we defined will be set to the target array. During this assignment, the toString function of notNumber will be called and causes the garbage collection of the array, as well as the allocation of a lot of uint32 arrays. And this is where the bug happens. Theoretically, the stale property was set to null and should not be accessible, but somehow the reference is still there. Some stuff internally did not properly check everything. This means that we have a reference into some memory where previously the R array was allocated, and we also allocated a lot of uint32 arrays, and we hope these now overlap. As I mentioned earlier, the uint32 arrays allow direct memory access. They can read and write raw bytes, while the R array was a complex object with JS values. Now it's already clear what you can do with this. You can use the uint32 arrays, which are accessible via buff, to read and write raw bytes at the location where the stale property thinks a standard JavaScript object is. So first we have to find if and how the buff and the stale array overlap. To do this, we can simply add a number to the first element of stale. But what is the first element of stale now? Isn't that garbage memory? Well, ideally, if everything works, it points where we created the uint32 arrays, and we populated that memory region with hex FFFF000 for 1 for 1 for 1 for 1, which is a JS value representing an integer, in fact the number for 1 for 1 for 1 for 1. This means now we add hex 101 to the first element of the stale array, making it the integer for 1 for 1 for 2 for 2. We can now simply search through the whole uint32 array memory buff looking for this for 1 for 1 for 2 for 2. Keep in mind that the buff has access to raw bytes, so it will also see the FFFF00 and the for 1 for 1 for 1. While the stale array thinks this is a JavaScript object and only uses FFF0 internally to determine that we have an integer and the value of it is for 1 for 1 for 1 for 1. So what can we do with this now? This is where exploitation really becomes creative. The Frag article says that once you have the ability to craft arbitrary JavaScript objects, you could craft a float64 array to create a read-write primitive. But QWERTY used a uint32 array. To quote him, here is his reason. It's easier than float to do math with, lol. And I guess he has a point. Floating point values in raw bytes are really annoying. So first of all, why do we want to craft a uint32 array? If you remember the basic structure of a uint32 array, it uses a vector to point to some raw memory. If you control where this memory points to, you can control where you can read data from and write data to, because it thinks it points to the actual array. There's a super clever way how to craft this array now. QWERTY creates a new object with 4 properties, A, B, C, D. He probably just took that from the Frag article, because when you look at how the simple object with only 4 properties is stored, it stores the values in line. This is very helpful in a second. As you see, the values set, like the hex 1 through 7, are simply placed here in memory after each other. So that's a very neat way to control a couple of consecutive values in memory. The two 64-bit values are the JS cell and the butterfly pointer. The JS cell, or more specifically the structure ID inside of the JS cell, determines what this JavaScript object actually is. In the Frag article, it looks like the object ID here has 136. So in order to craft a uint32 array, we would have to know the structure ID of that. According to the Frag article, this ID can change sometimes, maybe at restart or between different WebKit builds. But apparently it's very common to be 105. Nonetheless, because my exploit was very unstable, I tried to see if the value is maybe different, and the Frag article shows a technique how to do that. Back to the new object for a second. This will allocate a new object with 4 properties that look like this in memory. Hex 69, or in decimal 105, then 0, the pointer to the smash array, which we allocated way at the beginning, and hex 100. The function u2d is a clever little helper. As every number in JavaScript is basically a float, we can create a new data view of 16 bytes, so 64-bit, set the high and the low 32 bits, and return the float representation of those bytes. This new object creation will also override stale 0. Just a few seconds ago I mentioned that stale 0 points to a JS value representing a number, but now it was overwritten with a JS value representing a pointer to the JS object that was just created. This JS object it points to is not very interesting for us. It's not an arbitrary object we have crafted. But remember that the JS value with the pointer to this object is in the memory that is overlapped by the buff. This means we can use buff to manipulate the pointer. And what we do is we add hex 10 or decimal 16, which moves the pointer into the properties of the JS object. Now suddenly the hex 69 is the JS cell value, and the 0 here is the butterfly, and the smash address becomes the vector, the pointer where the actual array is in memory. To be clear, this points into the similar struct of that array, so this doesn't point into the memory location of that smash array, but also into this JS object struct with its vector, pointer, and its length. And hex 100 is the length of that array, which is actually just the object structure of the smash array. So now you know how we can misalign the pointer to this object, which will interpret the properties here as the actual object. We remember the original stale 0 pointer in stale 1 and then misalign stale 0. Then we can check the type of the stale 0 object. If it's not correct, we increment our structure ID guess and assign a new value to the stale 1a property, which will look like the structure ID from the misaligned pointer in stale 0. What we basically created now is we have two pointers in stale, which slightly overlap in memory. We also have somewhere an array called smash. We have also set the memory location for our crafted array, the vector pointer, to point to smash, to the smash structure, not the actual memory location of the smash array. This means we have another object that we can fully control. Stale is an array. The first element of stale points to a crafted uint32 array. So when we access the elements of that array, we obviously access the 32-bit values of the smash.js object structure. And as you know, the object contains 64-bit values. And the sixth 64-bit value is the length of the smash array. So stale 0 of 0 and 1 would be the first 64-bit, 2 and 3 would be the second 64-bit, 4 and 5 would be the third 64-bit, and 6 and 7 would be the fourth 64-bit. So with stale 0, 6, we can overwrite the length of the smash array. And we can now check the length of the smash array. Let's try this on the switch. We load the page and it might not immediately work, but it will refresh and try again. Okay, so we trigger the bug and we found overlapping memory by looking for 1 for 1, for 2 for 2. Now we check the current length of smash. We craft our object, then we change the length of smash and print the smash length again. And it changed. Isn't this crazy? So now we can just modify the vector where the smash array points to in the exact same way and then simply read the raw data it points to from the smash array or write to the smash array. It gives us a super simple access to the whole memory of the process. Next steps could be to find the address of the browser binary in memory to dump it. This video is already crazy long, so let's stop here for now. I really learned a lot working through the first part of QWERTY's exploit. I hope this also gives you a sense for how freaking complicated these modern memory corruption exploits are and what kind of work and knowledge is required to do them. I only scratched the surface here. I hope this also increases your respect for the people who do this kind of research. At this point, I also want to thank Retroid and Ando, who I just met on IRC and were in the same boat as me, and we helped each other trying to figure out how this works. And also huge thank you to QWERTY, who answered a lot of my noob questions and shared his progress with me. I really appreciate you supporting somebody who tries to learn this. If this sounds like fun to you, make sure you read the frag paper by Samuel Gross or Salo about attacking JavaScript engines, which gives you a way more in-depth insight into how this works. There's also another article more specifically about Firefox, which is different from WebKit, but also gives you a better idea how browsers work. Thank you very much, keep on hacking in the free world, and do.